Hello students, welcome you all. In NMR Spectroscopy, today I will explain about the factors which affect the chemical shift and magnetic anisotropy, which is also called as the anisotropic effect. In my previous lecture, I gave you the concept of shielding and deshielding and about the chemical shift. Now, so what I told you in my previous lecture, if the proton is surrounded by the electron, then it shields the if proton is surrounded with electrons, it means the electrons shields the proton, protect the proton, and it produces these circulating electron produces the local diamagnetic current, and this local diamagnetic current, it generates the induced magnetic field which opposes the external magnetic field, which is called as the diamagnetic shielding or diamagnetic anisotropy. So that I told you about the shielding and deshielding. Now suppose if electron density surrounding the proton if increases, it means if electron density surrounding the proton increases, it means shielding increases or shielding increases. And if shielding increases, then the induced magnetic field which is produced by this circulating electron, this will also increase. So this induced magnetic field, it will oppose the external magnetic field. Now, so if proton is surrounded by the electrons, then in that case the frequency, if shielding increases, if electron density increases, in that case the proton will resonate at lower frequency. It means, or we can say, the precessional frequency of the proton, it will decrease. So if electron density increase, then precessional frequency, if I say if I denote it by omega, in this precessional frequency this will decrease, and this precessional frequency, this is directly proportional to the chemical shift, or we may convert this frequency into the chemical shift that I told in my previous lecture. And so if this decrease, this is directly proportional to this chemical shift value, then this will also decrease. So simple. This main concept that we should remember when we discuss about the factors affecting the chemical shift. So if you will see this scale, then if this is TMS, which is taken as a reference at 0, the signal due to TMS, suppose it is coming up to be 0, which we arbitrarily take at a 0, and other signals, suppose this is 1, 2, 3, 4, 5, 6 and so on, like this, these signals are coming. So, and the signal may also go to the minus scale also. So it is 1, 2 and 3 and so on. So this is here, this is the lower delta value. This value at the right corner is the lower delta value, and this is the higher delta value. So this delta value is in terms of ppm, means we convert the frequency, the resonating frequency or precessional frequency in terms of delta. The instrument itself convert the precessional frequency into the delta, and signal we observe in terms of delta. So this delta value here, this is suppose electron density increase. If electron density increase, then in that case delta value will decrease. That I told you, means if shielding increase, then delta value, this will decrease. And if shielding decrease, it means the electron density decrease, then delta value, this will increase. So this region, this right corner region, this is called the shielded. This is called the shielded region, and this region is called the de-shielded region. This is called as de-shielded. Why it is called as shielded? Because if electron density increases, then in that case the induced magnetic field, this increase, which is also called the secondary magnetic field, this increases. So if this increases, then P induced, this will increase. That's why it is, if electron density increase, shielding increase, then this P induced increases, which is in terms of, that is called as the shielded. Okay, so or this is also called as the upfield. This is also called as the upfield here, and this is called the downfield. Because here you can see this B induced increases, means upfield. Here if electron density is less, B induced decreases and is called as the downfield. Now one of the factors which affect the chemical shift, that is the electronegativity. And now if electronegativity increase, suppose if we have CH3F, if we have CH3OH, if we have CH3Br, and so on like this, then in this case, as you can see here, the electronegativity value is increasing. Fluorine has the highest electronegativity. This CH3 is common in all, and here this fluorine is having the highest electronegativity. So if electronegativity increase, then what will happen? The proton, the electron density surrounding this proton, so it will pull the electron density towards itself. This fluorine, it will pull the electron density towards itself. If it pulls the electron density towards itself, then the electron density surrounding this proton, this will decrease. So if electron density decrease, or we can say shielding, this will decrease, and if shielding decrease, B induced, this will decrease, and if this decrease, then omega. Okay, if electron density is less, suppose if this is the proton and here this very less electron density is there, then the frequency, operating frequency that it will feel, it will more. And if operating frequency is more, then precisional frequency, it will start precessing with very high speed. So precisional frequency, that is omega, that will increase. So in that case, if lower is the electron density, in the same way, if this is a proton and a lot of electron density is very high, if electron density is very high like this, then it will feel this, the operating frequency that it will feel will be less. If operating frequency felt is less, then in that case this proton will resonate at a lower precisional frequency. So this is the main fundamental. So here this precisional frequency, this will increase as electron density is less surrounding the proton, and delta value, this will increase in this case. So this has the highest delta value. So if electron density, and this has the highest delta value. In the same way, if number of electronegative atom, if this increase, if number of electronegative atom increases, for example, we take the example, suppose if we have so if number of electronegative atom increases, what will happen? As you can see in this case, chloroform, this is having the highest electronegative atom, 3 electronegative atom. So if this increase, then it will pull the electron surrounding the proton much more. It will pull the electron more. So electrons surrounding this proton will decrease. So here the overall electronegativity is increasing. So if electronegativity is increasing, means the electron density is decreasing. Here in this case, the electron decreases much more surrounding the proton, or the shielding, this will decrease. And if shielding decrease, what I told you, if electronegativity is increasing, then electron density decrease, and same thing like this, B induced, this will decrease, omega, it will increase, and delta value, this will increase. So this will have the highest delta value. Here this is having the highest delta value in this case. Now third factor that we can write, that is, suppose if we hybridization, suppose, or before that, proton attached to the different kind of carbon. Proton which is attached to different kind of carbon. For example, the carbon through which the proton attached, it may be either primary, it may be secondary, or it may be tertiary. For example, if this is the proton which is here, this is one kind of proton, suppose this is another kind of proton, this is the another kind of proton. Three cases. Now if you will see here, then this proton is connected to the sp3 hybridized carbon. Sorry, this proton is connected to primary carbon. This is primary carbon. This proton is connected to secondary carbon. This carbon is secondary in nature. Here this proton is connected to tertiary carbon. This is tertiary in nature. Okay. So here the delta value. What about the delta value in this case? Delta value. If you will see in this case, the delta value is 0.9 ppm. Here the delta value is around 1.3 ppm. Here the delta value is around 1.7 ppm, like this. So next one is the van der Waals de-shielding. Van der Waals de-shielding. Now, so let us take an example. Suppose if we have this cyclohexane and these are the two protons. So this is simple cyclohexane, and here this all hydrogens, all protons will resonate at the same frequency. They will have the same delta value. So all proton are having same delta value. Okay. Whereas if you will see in this case, methyl cyclohexane. So this is your methyl cyclohexane. So in this case, the proton, this proton and this proton, they will resonate at a different frequency, and this all other protons, they will get de-shielded. So here, in comparison to this proton will get de-shielded. De-shielded means it will resonate at the higher frequency. Why it will resonate at higher frequency? This is statically hindered. The electron density of this proton is get hindered due to this methyl proton, and the electron density of this methyl proton and electron density of this proton, they will interact and they will repel each other. Due to this, the electrons surrounding this proton, this will decrease. So electron density will decrease surrounding this proton, and if electron density decrease, it means the shielding is decreasing. If shielding is decreasing, it means the delta values go to the higher value, that is de-shielded. So here this statically hindrance repel the electron density over proton. Okay, so this due to this repulsion, the electron density. So electron density decreases, and delta value increases. So this is the reason here. This is called the van der Waals de-shielding, and due to this van der Waals de-shielding means the surrounding group the electrons of the surrounding group, it will repel the electron of proton, due to which the electron density or the shielding around the proton will decrease, and if shielding decrease, then delta value will increase. So now, so next one, hybridization. Okay, so we know that if S character increases, this is the S character, then if S character increases, I should write S character increases, then electronegativity increases. We know that as the S character increases, electronegativity increases. For example, sp3 hybridized carbon is having the highest S character in comparison to sp2, and sp hybridized carbon is having the highest S character than sp2 and sp3. So if S character increases, electronegativity increases, and if electronegativity increases, then electron density that will decrease. Electron density decrease, it means, or the shielding that will decrease. If shielding decrease, then Bi, this will decrease, and if this Bi decrease, then, or if electron density decrease, then the proton will resonate at a higher precessional frequency, and the delta value will be also increase. So this is the simple thing. For example, if we compare this sp3, if any proton, if it is connected to sp3 carbon, or it is connected to sp2 carbon, or if it is connected to sp carbon, in this case, as you can see here, the electronegativity, this is increasing. If electronegativity is increasing, in that case, the proton which is in neighbor of this sp hybridized carbon, for that the delta value will increase. For example, suppose if you have this carbon, here this carbon, as you can see, this is connected to sp3 hybridized carbon. Now the second case, this proton is connected to sp2 hybridized carbon. Here this proton, if you will see, this is connected to sp hybridized carbon. Now this is having the highest electronegativity, this carbon is having the highest electronegativity, so it will pull the electron density of this proton surrounding the proton, that will, electron density, it will, or we can say this carbon will decrease the electron density surrounding the proton. This carbon will decrease less, and this carbon will be the least one. Okay, so that's why, as in this case, so for this one, suppose if you take delta value here, then in this case the delta value is around 2 to around 1.7, or sometimes suppose 2 ppm, 0 to 2 ppm is the delta value for this. Now for sp2 hybridized, so what should be the trend? Trend should be, this should be lowest delta value, this should be having the highest delta value, and this should having the more one. So, but here the trend is little difference. So in this case, this is having the delta value of around 4.5 to 6 ppm, whereas this the proton which is connected to sp hybridized carbon is having the delta value from 2 to 3 ppm. So here we have the exception. Here we have exception, and this exception, this is why reason is there, due to magnetic anisotropy. So this difference is due to magnetic anisotropy. Now let us discuss in detail about the magnetic anisotropy. So what do you mean by this magnetic anisotropy? So why this difference is there? Why this difference is there? So we will now see about the magnetic anisotropy, or it is also called as the anisotropic effect. So such type of magnetic anisotropy, as you can see here, where this is alkene, this is alkyne. So where it has been seen, it is seen in case of, it is seen in aromatic compound having the benzene ring. Then in case of alkene, in case of alkyne, aldehydes, nitriles, like this. So in such compounds, etc., they are seen. Now what is this magnetic anisotropy or anisotropic effect? So anisotropy means this is just the opposite of isotropy. Isotropy we can understand in one way, that is uniform. Isotropy means uniform, same type, and anisotropy means non-uniform. So this is directly connected to this non-uniform magnetic field. So when the secondary magnetic field, as you know, the circulating electron, they produce a secondary magnetic field, and this secondary magnetic field, it is sometimes not uniform all over the molecule. In some place it may be, in the secondary magnetic field, it may be parallel to the external magnetic field, or in other place the secondary magnetic field, it may be opposite to the magnetic field. So this is called as the anisotropic effect. So you will more understand it with the help of example. So first of all, what is this anisotropic effect? The circulating electron, what we can write, what is this definition? The circulating electron surrounding the proton produces induced magnetic field, which is also called as the secondary magnetic field or secondary magnetic field, which is not uniform which opposes the external magnetic field, and this is not uniform. So just the opposition, this is not uniform. So which opposes the, what I should write, which opposes the external magnetic field in non-uniform manner. Okay, so sometimes it is parallel to the external magnetic field, and sometimes it opposes the external magnetic field. Sometimes it is parallel to external magnetic field, whereas sometimes it opposes the magnetic field. So this is called as the magnetic anisotropy or anisotropic. So for example, in benzene, so we may show this anisotropic effect. Now, so these are the protons, 6 protons which are present, and these are the pi electrons, and these pi electrons in presence of this external magnetic field. These pi electrons, these are the circulating one, and this circulating pi electron, it will generate a local diamagnetic current, or we can say the secondary magnetic current. So this secondary magnetic field is generated, and it is generated in such a way that here in this region, okay, inside this ring, this if region inside the ring is it shielded the magnetic field which is coming out from this region, that is inside the benzene ring, it opposes the external magnetic field, and region which is outside the benzene ring, it is parallel to the external magnetic field. So as here this region which is outside the benzene ring, this region and this region, this is parallel to the external magnetic field. So that's why this region is called as the D-shielded region. D-shielded region, or we may call it a paramagnetic zone. So here this zone is paramagnetic zone. Now here, as you can see, the region inside this ring, here this, suppose this is the B induced or secondary magnetic field. Here this opposes the external magnetic field. So here this region we may call it a shielded region, or it is called as a diamagnetic zone. Okay, so as we can see that in benzene all protons are present in a D-shielded region or paramagnetic zone. So these protons are shielded one. That's why they will resonate at a higher frequency. Means they will come. Means their chemical shift, that will be the higher chemical shift. So the delta value for this proton, it comes from around 6.5 to 8.0 ppm. This is the delta value for these phenyl proton. Okay, so we may show it in another way in terms of this cone also. Suppose if this is benzene ring and these are the protons. So we show in terms of this cone, we show like this. Okay, so means here the inside the cone is the shielded zone. So shielded zone means this plus. This plus, it tells about that is it is the shielded zone. Shielded zone, that is inside the cone. Inside the cone is the shielded zone, whereas outside the cone, where I have written this minus, this is D-shielded zone. Okay, or it is, we may write outside cone, outside the cone. Right. So here we may see this anisotropic effect. Why it is called as anisotropic effect? As you can see, inside the cone, the secondary magnetic field is opposing the external magnetic field. Outside the cone, the secondary magnetic field is parallel to the magnetic field, means this is not uniform in this case. So that's why we may see the anisotropic effect in case of benzene. In the same way, if you will see for alkene, suppose, so to this example second, if you have this alkene, now in alkene, how we can show this anisotropic effect? So these are the proton. These are the protons. And if you want to show this anisotropic effect, then you can see these are the pi electrons. Pi electrons are circulating in this way, and this circulating pi electrons, it will generate a local diamagnetic current, or we can say it will generate a secondary magnetic field, and this secondary magnetic field in this way it will generate. And this secondary magnetic field, the direction of the secondary magnetic field is this, like this, is the direction of a secondary magnetic field. Okay, and external magnetic field, because it will generate a LDC, that is local diamagnetic current, in presence of this external magnetic field. Okay, and this Bi here, as you can see here, in this region means within this region, within this pi bond region, the secondary magnetic field will oppose the external magnetic field, whereas this outside this region where these protons are present, this secondary magnetic field, it is in parallel in the direction of the external magnetic field. So here it means these four hydrogens in case of alkene, they are present in d-shielded region, or we may say this is the paramagnetic zone. And here this region where no proton is present, this is the shielded region. In shielded region, as you can see, no proton is present. So since these protons are present in d-shielded region, so here this delta value, in this case, delta value for this alkene, and this is around 4.5 to 6.5 or 7.0. So this is the delta value for alkene, and this is lower than that of the phenyl proton, because the phenyl proton are more d-shielded in comparison to this alkene proton. And we may show here, if we want to show the this cone for this one, then we may show the cone like this. Here again, this is where this is the shielded zone. Here this is the d-shielded zone, minus it denotes the d-shielded zone, and at d-shielded zone all these four protons are present, which are the d-shielded, and due to this d-shielding, the delta value, that is chemical shift, is coming out to be 4.75 to 7.0. Now what about the alkyne now? So if you see for alkyne, okay, so this alkyne, what I told you, if I say the proton is connected to sp3 hybridized carbon, or proton may be connected to sp2 hybridized carbon or sp hybridized carbon. So if proton is connected to sp3 hybridized carbon, then delta value it is 0.7 to 1.7, or 0 to around 2, or 0 to 2. Now, like if suppose sp3 hybridized carbon, if this is connected to sp3 hybridized carbon, here the delta value, this proton is connected to suppose sp2 hybridized carbon. In this case, you will see the proton is connected to this sp hybridized carbon. So this is sp this is sp2 and this is sp3. So which is more electronegative? sp hybridized carbon is more electronegative. If sp hybridized carbon is more electronegative, then it should resonate at the highest. This is more electronegative. It will pull the electron density towards itself. It will pull the proton electron density which is surrounding the proton towards itself more. That's why the delta value in this case should be higher than that of this, Okay. So, but for here, if you will see, the delta value is 0 to 2 ppm, whereas in this case the delta value is 4.5 to 6.5 or 7 ppm. Suppose what I have written over here, and here the delta value is around 2 to 3 ppm only. So according to this electronegativity concept, this delta value should be higher, but here this delta value is lower, and this is due to the anisotropic effect. So how can we show this anisotropic effect in alkyne? So suppose if you have this alkyne, then how these protons are shielded one. Why this is means these protons are quite shielded one, that's why they are coming to the lower delta value. So these protons are shielded and we can show it, and as I told you, these electrons, this circulating electron, here electrons are circulating in this way, and this circulating electron, it will produce the local diamagnetic current, or it will produce the secondary magnetic field. So in presence of this external magnetic field, these are electrons, pi electrons are moving, and it will produce a secondary magnetic field, that is Bi, or induced magnetic field. So here, as you can see, this is the secondary magnetic field. This is the direction of the secondary magnetic field, like this. Okay, and here this is the direction of this Bi, that is induced magnetic field or secondary magnetic field. Now, so what you can see here, this Bi is opposing the external magnetic field, so that's why this proton which are present over here, they are quite shielded one. And in this region no protons are present, so this is the de-shielded region, and this is the shielded region. This is here the shielded region where these protons are present, or we can say this is the diamagnetic zone. Here this is the de-shielded region, no protons are present, which is called as the paramagnetic zone. If you want to show in terms of this cone, then we may show like this. So here this is a plus, and here this region is the plus region. This is the shielded region. This is the shielded region where the electron density, where proton is present. So that's why these protons are shielded, and the delta value for this proton, it comes to be 2 to 3 ppm, like this. Now, in the same way, if you want to show for aldehydes, then in aldehydes, how we can show this anisotropic effect? So, anisotropic effect, where there is a non-uniform secondary magnetic field or non-uniform induced magnetic field. So, if you see the aldehydes, or suppose this is your aldehyde, this is the aldehydic proton, and here this pi bond being the loosely held electron, in presence of external magnetic field, it will start circulating like this. There is circular motion of this electron, and this motion, it will create a secondary magnetic field. This will create a secondary magnetic field like this, and you can see this proton here, The proton is lying in a d-shielded region where the secondary magnetic field is parallel to the external magnetic field. So here this proton is present in d-shielded region, or this is your paramagnetic zone, whereas you can find no proton is present in this region. No proton is present in this region where the secondary magnetic field is opposing the external magnetic field. So that's why these aldehydic proton are quite d-shielded, and delta value it is very high delta value, 9 to 10 ppm is the delta value for this aldehydic proton. Okay, if you want to show in terms of this cone, then in the same way like that of, so this is the shielded region where no proton is present, and here this is the d-shielded region where you can see the proton is present and it is quite d-shielded, so that the delta value is very high, that is 9 to 10 ppm. So these are let us see some more examples of anisotropic effect. So what we have seen, usually the protons are, it may be somewhere it may be shielded, somewhere it may be de-shielded, and up to now what you have seen that the shielded protons usually comes near to 0, that is 1, 2, 2, 3 like this. Now there are some exceptions where the protons are so much shielded that the delta value will go at the negative side also. So let us see some examples. So if you see the example of 18-aniline system, so in 18-aniline system, if you will see, then some of the protons are quite shielded and some of the protons are quite de-shielded also. So this is the structure of this 18-aniline. Okay, so this is one of the pi bond, 1 pi bond, 2 pi bond, next conjugate, this is 3, and then 4th pi bond, and this is 5th pi bond, 6th pi bond, 7th pi bond, okay, 8 pi bond, and this is 9th pi bond. So 9 pi bond and 18-aniline system, and this here you can see these are the 1, 2, 3, 4, 5, 6 hydrogens which are present in a inner zone, and these are the protons which are the outer proton. These protons are the outer proton. These are the outer protons. Now this aniline is a aromatic system. It is, why it is aromatic system? Because it completely follow the this Huckel rule. 4n plus 2 pi electrons are present over here. It is completely planar, delocalization of electron, complete delocalization of electron is there. Now in presence of external magnetic field, if you have an external magnetic field, then in presence of this external magnetic field, these pi electrons start circulating, and this in a circular manner like this, they are circulating pi electrons, and due to this motion of this pi electron like this, these are circulating in this manner, they are circulating. So they will produce a induced magnetic field, and the direction of induced magnetic field, if you will see, this is the direction of induced magnetic field like this. Okay. So what we may see here, so if you will see, then inner protons, so these inner protons, they are in the region of shielded region. So here, this region Bi is the induced magnetic field, which is opposing the external magnetic field. So these inner electrons are very much shielded, whereas these outer electrons, these are the outer electrons which are de-shielded ones. So this is the de-shielded region. This is the de-shielded region, or de-shielded protons, we can say, diamagnetic zone. And here these inner protons, they are quite shielded. Okay, shielded region, they are coming in a shielded region, and outer protons are in a de-shielded region. So they are inner protons are so much shielded that delta value in this case, it comes to be negative, around -1.8, like this delta value. So it goes in a negative side, means it is go below the TMS, because TMS is taken as a 0, it goes below the TMS. Whereas this outer proton, it is de-shielded, quite de-shielded, they are also de-shielded, and it is coming from 7.5 to around 8.9, 8.1, like this. So this around 8, and the delta value comes. So this is about the 18 aniline system, which is the aromatic system, completely planar. As it is a completely planar, so that's why the inner protons are shielded one. Inner protons are shielded, whereas the outer protons are de-shielded. Now, if you will see 14 aniline system, suppose if I draw this 14 aniline system, then this 14 aniline, this is also the aromatic system, complete aromatic system, and okay, so here this one is the now, so here this outer protons and the inner methyl protons are present over here. In 14 aniline, these are the outer protons, and inner protons are present in the methyl group. Inner protons are present in the methyl group. And now let us see if this is our So how many pi bonds you can see? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. That is 14 aniline system. So this is 14 aniline system. Okay, so this 14 aniline system, and if you will see the anisotropic effect over here, then these circulating electron, again these electrons are circulating, these pi electrons are circulating, conjugated system, they are circulating one, and they are circulating in this way, and these circulating electron, they will produce a secondary magnetic field like this. Okay, they are producing the secondary magnetic field, and in presence of this external magnetic field, they are producing the secondary magnetic field. And as you can see, the inner protons, inner methyl protons are quite de-shielded. So these protons are, methyl protons are de-shielded. Sorry, methyl protons are quite shielded proton, and the delta value, it comes to the negative, and this is quite negative, around the delta is -4.5 ppm, so much lower value, it goes to minus. And these are the outer protons, These are the outer protons. Outer protons are the shielded ones. Outer protons are d-shielded ones. Outer protons are d-shielded and they comes around delta around 7 to 8 or 8 around 8 ppm like this. So this is about the 18 aniline system. In the same way, we may see some 10 aniline system also. So 10 aniline system. Okay, so 10 aniline system like this. So here we have hydrogen, CH2 hydrogen. These are the CH2 hydrogen. So 5 double bond, all this completely delocalized, follow the Huckel rule. So this system is also an aromatic system. This is also aromatic system, and this will here, these CH2 protons here, they are, because they are inner protons, they are shielded ones. These are quite shielded protons. Okay, these are quite shielded protons, and it comes around, because we know this CH2 proton, it comes around 1 or 1.2, around 1.3. So delta value in this case from 1.3 to like this, or it around 2 ppm, we say 2 ppm. It is close to the 2 ppm, approximately like this, because the CH2 proton, it is the CH2 protons comes like this. Now these are the all other this proton, they are the benzene aromatic proton. This is the aromatic proton, and they resonate at this is d-shielded. They are quite d-shielded one. So these protons are d-shielded one. So if you will see the ring current, so it is in this way, like this, and here this is in a inner, it is inside inner ring. So inner ring proton, you can say it is inside the zone, inside the shielded zone. That's why it is resonate at this position where this one. Okay, so this is the 10 aniline system. Now suppose if another aniline system, if you draw another aniline system, which is also a 10 aniline system, and no. So in this case, this system is non-aromatic. This is a non-aromatic system. Why this is non-aromatic? Because these two hydrogens are not planar. We know that all the aromatic system are the planar system, but due to these two hydrogens are two inner hydrogen atom are not non-planar, we can say non-planar, and due to this it behaves as an olefinic system. It will not behave as an aromatic system, and we know that this aromatic proton, it resonates at a very high highly de-shielded, and comes at around 6.5 to 8.5, but it behaves as an olefinic system. So it behaves as olefinic system. So as it behaves as an olefinic system, so the delta value in this case is similar to like that of alkene, which I told you from 4.5 to 6.5 ppm is the delta value for this. Okay, so these are few examples for this magnetic anisotropic. Okay, thank you.